Attempts have been made at using multigrid methods for cloth simulation, yet it is difficult to design these methods to perform optimally across a wide range of problem sizes, especially when constraints are introduced. In this paper, we propose a class of multigrid solvers to simulate cloth at superior performance levels. To illustrate the problem, we first want to highlight the inherent anisotropy for a simple piece of cloth falling, and show how it changes over time and space. Initially, it has no velocity and is lying perfectly flat. The effects of gravity will pull it down and introduce bend, shear, and strain forces. After discretization of the problem, multigrid solvers have to deal with the linear system that has been formed. And if coarsening is done per node, then it is important to be able to understand which nodes are strongly connected in the graph of the matrix. We visualize this in UV space, where strong connections between vertices are blue, relatively weak negative connections are shown in green, and positive connections show up as red. Connections that multigrid would consider weak in coarsening are omitted. For each vertex, there are actually 3 connections to consider, corresponding to velocity in the x, y, and z directions. So for the first frame, we can see that without the presence of any buckling or bending, that the x layer is purely anisotropic in that axis, and the z layer is purely anisotropic in that direction. At the start frame, the y layer picks up the anisotropy from one of the 2 directions, since there is no buckling to couple the unknowns yet. Once the cloth has started to move, all the layers now exhibit anisotropy that changes direction throughout space, posing difficulty even in a scalar problem for geometric multigrid methods. Algebraic multigrid methods can handle this changing anisotropy for a scalar problem. However, for a problem with different directions of anisotropy for each unknown, it is difficult for AMG to form a coarse grid and an interpolation operator. To address this problem, we present a method in our paper for cloth simulation based on smoothed aggregation. To demonstrate the performance of our method, we first consider a number of examples constructed to highlight different types of problems. The simplest of these is a membrane which is held fixed along the boundary, but subject to gravity. The next one continues to be an approximation of a well-formed PDE, but introduces large deformations.
In our third example, we introduce a reentrant corner, which is known to introduce a singularity in the PDE. This makes it more difficult to solve.
Across these 3 examples, we see speedups across a wide range of resolutions, material parameters, and simulation settings. As expected for multigrid methods, the speedups are best for larger resolution problems, but even for small problems, the speedups can be quite significant for stiff problems or large time steps. Our algebraic approach handles cloth object collisions at no extra cost and with no change to the underlying collision handling approach. A popular way of handling cloth-cloth and cloth-self collisions is by adding repulsion springs. Our algebraic approach once again handles these without any modifications, although at a small additional cost because they aren't accounted for in the original PDE and therefore in the multigrid treatment. As a final test, we ran our smoothed aggregation solver on a full character. In this example, there are 371,000 vertices, and we obtain a speedup of about 6 to 8 times for the linear solves compared to a block diagonally preconditioned CG method. This includes both the time to set up the multigrid hierarchy as well as the time to solve the equations using this hierarchy.